All right, folks. Today's lesson is going to be on the binomial distribution. The binomial distribution is used to calculate the number of successes in successive independent trials of an experiment with two possible outcomes. So that's kind of a big definition. There's a lot to unpack there. The main idea is that binomial distribution only works when you run an experiment that has two possible outcomes. So think like flipping a coin, right? It could either come up heads or it could come up tails. Um, there's other situations that just happens to be the most common. This is the way we calculate the binomial distribution. So you type into Desmos binomial dist, and then you'll put in N, P, and R. It'll give you the option to type in the min and the max, and I'll show you an example of that in just a second here. What Desmos is doing when it calculates a binomial distribution is it's taking a combination, right? So that's the first part of this formula. And then it's taking the probability of a success times the number of successes, and then 1 minus p is the probability of a failure, and n minus r is your number of failures. And then this is just that same formula written a different way. Remember that the number of combinations, the way Desmos actually calculates that is n factorial over r factorial times n minus r factorial. But the second part of the formula is the same as what's written over here. Now, these are three different ways to calculate the value of a binomial distribution. They will all give you the same answer. Let's kind of unpack a little bit what the different variables in here mean. I've kind of talked about some of them already. N is the number of trials. So we can see that in the first formula in the binomial distribution. That's the first number that we would type in the parentheses. In the second formula, we type in n two places. So we put it in the combination formula. And then we also use n to calculate the number of failures at the end of the formula. And then same thing with the expanded version of that. We put in n factorial on top and n minus r factorial on bottom of the fraction, and then we take that to the n minus r power. Okay, so that's what n represents as the number of trials. R represents the number of successes. And so we can see that in the first formula down at the bottom, we put in R for our min and our max. In the second formula, we put it in the combination. We put it in the exponent of both of our formulas. One, we just put it by itself. The other one, we're subtracting it from subtracting it from n. And then it actually shows up in 4 different places in the expanded version. So on bottom we have r factorial and n minus r factorial. We have it in the exponent of p, and in the exponent of 1 minus p, where we're subtracting it from n. Okay. And then last is our probability of a successful trial. That's the last thing that goes into our formula. So we can plug it in the binomial distribution formula. It's the second number, right? It comes right after n. It shows up in 2 places in the combinations formula. So we raise p to the r power, and we raise 1 minus p to the n minus r power. And then it also shows up in 2 places in the expanded version, because again, we take p to the r power and 1 minus p to the n to the r power. Okay, so in general, you're not going to have to use the second two formulas. I just want you to understand what Desmos is doing when it calculates the binomial distribution. Let's talk about, let's go through an example problem and talk about how we would plug into these formulas to get the probability. Okay, so binomial distribution example number 1, Mr. Brunswick flips 4 fair coins at the same time. What is the probability that 2 of them land on heads? So I've got a probability tree drawn out here. You can see the first coin can be heads or tails, the second coin can be heads or tails, third coin can be heads or tails, fourth coin can be heads or tails. And so that leads us to 16 different outcomes. Right? It could be heads, 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 tails, heads, tails, heads, 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 tails, tails. I'm not going to read them all, but you can see the 16 possible outcomes for those 4 coins. Okay, so then what we're going to do is we're going to make a table. We're going to count the number of ways that we can get 0, 1, 2, 3, and 4 heads, and then we'll use that to calculate the probability of getting that amount of heads. Okay, so to get 0 heads, well, there's only one way to do that, right? That's when you get 4 tails, there's only one possible outcome for that, so you have a 1 in 16 chance of getting 4 tails. You have a 4 in 16 chance of getting actually, now I'm not sure that I said that right. You have a 1 in 16 chance of getting no heads. You have a 4 in 16 chance of getting 1 heads. So you could go tails, tails, heads, tails, tails, heads, tails, tails, heads, tails, tails, or heads, tails, tails, tails. So you got a 1 in 4 chance of getting 1 head. You have a 6 in 16 or 3 in 8 chance of getting 2 heads. Right? So those are those 6 options listed out right here that I have highlighted. And that's actually the answer to the question, so we'll come back to that at the end because that's what I was asking. What's the probability that 2 of them land on heads? I'm going to do the entire distribution here because I want you guys, because I'm going to ask some more questions later and it'll be useful to have that entire distribution written out. If you want 3 heads, so that's sort of like the same as getting 1 heads, you have a 1 in 4 probability of that, or 4 in 16. And then 4 heads, that's the same as getting 0 heads. You have a 1 in 16 probability of it. Okay, so hopefully that makes sense looking at all the outcomes. Now let's talk about how we would calculate that using the binomial distribution calculator. Oh, right, sorry. And then to go back to the question, what is the probability that 2 of them land on heads? That's the middle value in the table, right? There was 6 opportunities to get 2 heads. So let's talk about how we calculate that with the calculator. First way we would do that is we're putting in 4 for n. That's the number of experiments, right? The number of trials. We flipped 4 coins. 0.5, that's the probability of getting a heads, right? So with 1 coin flip, you have a 50% chance of getting heads. And then our number of successes was 2. We're looking for the probability that you get 2 heads. So this is one way you could type this into Desmos. You could also type it in with this formula. So again, 4 trials, 4 coin flips, 2 heads. 0.5 is your probability of getting a head, so we're raising that to the 2nd power. 1 minus 0.5, that's your probability of not getting a heads, and so we're raising that to the 4 minus 2 power. And then we can also see that with this formula where we've expanded out the combinations using factorials. So that's 4 factorial over 2 factorial times 4 minus 2 factorial in the denominator. Okay, and you can plug all of these into Desmos And you can see for all of them, you get 0.375. If you turn that into a fraction, that is equivalent to 3/8. Note that when you type in the binomial distribution into Desmos, you need to click this check mark, find the cumulative probability. Okay, so that's my first example. Let's try a second example. In this one, Mr. Brunsvold flips 4 fair coins at the same time. Now I'm looking for what's the probability that 3 of them land on heads. So I've got my probability table. I'm looking for 3 this time, so I can see my answer is going to be 1/4. Okay, so if I type out my binomial distribution, again, I'm running 4 trials, and again, my probability of a success is 0.5. So the only thing I'm really changing this time around is my R value, right? Because now I'm looking for 3 heads instead of 2 heads, so I'll change those R values to 3. We can see that also in the expanded combinations formula, right? So we have 4 coins. We're choosing 3 of them to land on heads. We have a 50% probability of getting any coin landing on heads. So 0.5 to the 3rd power and 1 minus 0.5, that'd be your probability of getting tails, to the 4 minus 3 power. We can also do that with the formula that expands out the combinations into a factorial. And again, we can type all those into Desmos, and with all 3 of those options, you get 0.25, which is of course equivalent to 1/4. Okay, so hopefully this is making sense. And again, remember, the only one that you really have to know how to use is the first formula, but I'm just showing you the second formulas to show you how the Desmos calculator actually works. Okay, binomial distribution example number 3. Mr. Brunsvold again flips 4 fair coins at the same time. What is the probability that more than 1 coin lands on heads? Okay, so let's take a look at our distribution. We're going to look at all the options where we get more than 1 heads. And it just so happens that it's these 3 options right here, right? And you can look down, check all of mine, and see that in all the ones that I've highlighted or boxed, there is more than 1 heads in those examples. And in all the ones that I did not box, there are either 1 or 0 heads. We can see that there are 11 options here, so our probability ends up being 11 out of 16. We can calculate this with the binomial distribution. Now note that I'm not using the other formulas at this point. The real advantage of the binomial distribution function in Desmos is that you can calculate a range of values. I know that I want between 2 and 4 heads. That's what I want to calculate. So it will actually calculate all 3 of those at once if you put your minimum at 2 and your maximum at 4. Pretty convenient. Plug that into Desmos, and we'll end up with 0.6875, which happens to be equivalent to 11/16. Okay, a couple more examples. Now we're going to change it up a little bit. Mr. Brunsvold flips 12 coins at the same time. So you can imagine with 12 coins, you don't want to draw a probability tree. That's going to be a really big tree. These coins are all weighted and have a 60% chance of landing on heads. So the other reason why you don't want to draw out a probability tree is even if you spent all the time doing it, not all the options on the tree have the same probability of success, right? Because the options where you get more heads are going to have a greater probability of success than the ones where you get more tails. What is the probability that 7 coins land on heads? So we're just going to jump straight to the formulas this time. Let's start off with the binomial distribution. So it's binomial distribution. We're flipping 12 coins, so I'm putting in 12. And the probability of getting a heads is 0.6. And then I want to know the probability of getting 7 heads. So I'm putting in 7 for my min and 7 for my max. I can also calculate this using the combinations formula. So again, 12 coins, I'm looking for 7 heads. 0.6 is my probability of getting a head, so 0.6 to the 7th power. 1 minus 0.6, that's my probability of getting tails. And then 12 minus 7 would be the number of tails that I would have to flip, or 5. Right? And then this is just the version where we expand the combinations using factorials. With all these answers, we get 0.227. I can also calculate this the other way around. What do I mean by that? Well, when you're doing binomial distribution, you kind of have to define what a success is. It might be useful to think about this as a success being flipping tails. So if I want to know the probability that I get 7 heads, that means I had 5 successes. I flipped tails 5 times. So my binomial distribution, I'm still doing 12 trials. A success is flipping tails. This is my probability of flipping tails on this weighted coin. And I need to do it 5 times. And so you can see I can write this out using the combinations formula, right? So 12 trials, 5 successes. Probability of flipping tails is 0.4. So I'm raising that to the 5th power because I want to flip 5 tails. 1 minus 0.4. That's 0.6. That's your probability of flipping heads to the 12 minus 5, or 7th power. And we can also do this with factorials. You could type any one of these 6 formulas into Desmos, and they would all give you the same answer, 0.227. Okay, last example. Mr. Brunswold flips 12 coins at the same time. These coins are all weighted and have a 60% chance of landing on heads. What is the probability that between 9 and 11 coins land on heads? So for this one, we're going to skip the second 2 formulas because they're not going to be useful. We're only going to use the binomial distribution. I'm flipping 12 coins. I have a 60% probability of heads. And I'm going in between 9 and 11, right? So again, this is the advantage of the binomial distribution function in Desmos is historically you would have had to have calculate 9 and 10 and 11 to get this answer. With the binomial distribution, you can just type in 9 and 11. Your answer will come out to be 0.223. We can also calculate this the other way, so I can assume that a success is actually flipping tails. So if I flip 9 heads, that means that I flipped 3 tails. If I flipped 11 heads, that means that I flipped 1 tail. So 12 trials, 0.4 is my probability of flipping tails, and I'm looking for flipping in between 1 and 3. This will spit out the same answer in Desmos. That is it for this lesson. I hope it wasn't too long or confusing. If you have any questions, please ask. Go ahead and try the binomial distribution quiz in Schoology.